Syzygy episode 83, James Webb set for launch? Yes, honestly. And welcome back to another edition of the Syzygy podcast, a very exciting edition of the Syzygy podcast because we're back in the same room again. Emily, you're actually literally right there in 3D, only 1.5 meters, let's call it 2 meters for social distancing purposes, away from me in real life. Hello!
Hello, I can see angles of you that I haven't seen for 18 months.
I know, it's been 2-dimensional and now it's 3-dimensional again and it's so excited. For all of you people who are out there in listener land who are still in lockdown world, our commiserations. Here in the UK, we're allowed to do this. We got the window open here in Emily's office, which means that if you hear geese flapping and squawking and cars driving past and lawnmowers and so on, it's because we're trying to keep the air flowing, which is what we do in this modern corona phase of the world. But
at the recommended
together.
rate of 10 litres per person per second.
Wow, you've got all the stats. Emily's got all the stats on that. But that means we can be together, which is so nice because it's been a really long time. Do you know what else has been a really long time? Since our last episode, which is looking at the website and he giggles. A bit awkward. It was July. And look, we're really sorry. All of you fans out there, all of you listeners out there, we know it's been a bit quiet. You know what? Summer's always a bit of a weird time anyway. But summer, when the world's going through waves hands, all this is even weirder. So tell you what, make you a deal. We're back and we're going to do our level best to get back into some kind of real routine again. I'm not going to make any promises, but Emily, what do you reckon? Do you think we can try to get something out at least vaguely regularly?
It's a regular recurring event in my calendar now. So
Fantastic.
That's the thing.
That means something.
I have to do what my calendar says.
If anyone knows Emily, you know that that's a big deal. So if we're going to be back and do a big welcome back show, then we may as well pick a really big topic. And there's no bigger topic in the world of astronomy and space right now than the impending launch of a particular space telescope. Emily, what are we talking about today?
We're talking about our good old friend JWST, or the James Webb Space Telescope.
I cannot believe we are actually doing this because this has actually been a joke in this podcast since we began, I think. Every once in a while we would refer to the JWST, the James Webb Space Telescope, as kind of one of those, well, I mean, that'll happen before the James Webb Space Telescope takes off. Like it's just, it was never going to launch. It's been delayed and delayed and delayed and delayed and delayed. And here we are. We actually have finally a launch date.
Exactly. I've been teaching first year astronomy for the better part of probably 10 years now.
Yeah.
It's always been 2 years away.
It's a little bit like nuclear fusion in that regard. It's only 30 years away, and they've been saying that for about 60 years now. JWST is 2 years away, and they've been saying that for the best part of a decade or more. So apparently it's not 2 years away. It's 2 months away.
Yeah, so we're looking at now a launch date of the 18th of December.
Which, can I just point out, and look, this isn't a hint to anyone, that's my birthday, right? So I'm really not suggesting that any listeners do anything special for me on that day. It's not about me being my birthday. You don't have to do anything at all for me. You really don't, in case you were thinking of it. But as an extra celebration, it's the launch of JWST. So tell you what, if you did want to do something for me, tune in and watch that launch and keep your fingers crossed. Because if it gets up there safely in one piece as designed, then that'd be a really, really nice birthday present for me. And if it explodes on the launch pad, that'd really suck for everyone, including me on my birthday. So fingers crossed, December 18th, the thing's finally going to launch. Emily, what is the JWST? It's a space telescope. Haven't we already got one of those?
No, this is the space telescope.
Oh, sorry. Did I not quite emphasize that correctly?
So we got very, very excited, of course, when Hubble went up. Well, some people more than others. I was sort of a little bit unawares because I was busy learning my times tables at the time.
It was a while ago. When did Hubble launch?
In 1990.
Wow. And even then, that was quite late.
Yes, that was delayed by a few years at that point already.
Yeah.
So we probably started getting kind of the real famous Hubble pictures and so on from about 1995. And since then, it's just completely revolutionized all of astronomy. And JWST is about to do that again, but more so.
Yeah, again, but bigger. Now, Hubble, I think I read right, was originally supposed to launch in 87. or maybe even 86, and was delayed by like a really long time, finally launched in 1990 and way over budget. There's no way that the space astronomical community could possibly mess up on that scale again. Is there?
Yeah.
Shall we have a very quick potted history of like when was the JWST supposed to originally launch?
Oh, now you're testing me. Was it? It was about 2004.
Something along those lines. It's sort of, in the 2000s. Yeah.
I mean, it probably depends on whether you go back to the early kind of, here's a great idea, let's do Hubble, but again, and bigger and better and more exciting. The whole telescope over this kind of checkered-ish history of being built has actually changed, I think, quite a lot, because the science has changed as we've gone along.
Yeah. I mean, isn't it the case that it was one of these grand projects that you get in science every once in a while where we're going to do the thing. Do you know how to build that yet? No, we haven't got the technology to do that. We're just going to pitch this one forward by a decade and assume that along the way, we're going to work out a whole bunch of stuff. See the square kilometre array, for example. They have no idea how they're going to do the computing on that one still. But you can do that in science as long as you make a reasonable pitch forward in your conception of the technology and think, we'll probably solve all of those, but there'll probably be a bit of a tweak along the way.
Yeah, exactly. And you think about kind of the history as well. So NASA had this great observatories program, which was one of the most beautiful programs, I think, that we've done in astronomy, because NASA just went and said, hey, we've got this thing. It's the electromagnetic spectrum. That means we get light from all these different parts of the spectrum, from X-rays, gamma rays, ultraviolet, optical that we see, infrared, all the way down to radio wavelengths. They said, let's just build space telescopes that go and investigate that spectrum.
Yeah, one of each, or maybe a few that sort of, overlap, but let's cover all of that.
Yeah.
So what were the big ones that we've had so far?
So we had XMM Newton and Chandra, which were looking at really, really high energy stuff.
So that's X-ray stuff and gamma ray stuff?
X-rays and gamma rays, yeah. We had Hubble, which was, of course, the optical and did a little bit of infrared and ultraviolet as well. We had Chandra and the infrared. And then as a follow-on to Chandra, we had Herschel, which was in the earlier 2000s. So we're now coming back, I guess, on ourselves, because radio observations we do largely from the ground. You don't need to put a thing in space for that.
Sure.
So.
We got that covered on the ground. That's fine. Big dishes, yeah.
Yeah. So all of these, apart from Hubble's the only one that's still running out of that program, intentionally, if you like. Hubble's just one of these telescopes that just keeps going.
Keeps on going. Which, given the
lifetime.
trouble that they had getting it up there in the first place, because wasn't there like a mirror problem and stuff?
Yeah.
Like, well, let's not go into that, but read up on it, kids. It's fun. What happened way back when Hubble got launched. Oh no, we did the mirror the wrong shape, they said. Given that there were all those problems and it went over budget by some ludicrous amount, as these things do, it's kind of nice that it's still going and quite kind of extraordinary that it's still going.
It's not just still going and kind of, look, here's our lovely little antique Hubble going on.
Yeah.
We're getting something like 120 gigs of real science data a week from
That's a
Hubble.
lot.
Yeah.
That's a lot of gigs.
When you think this is a thing that was built back in the 80s.
Yeah, they didn't even know what a gig was in the 80s. They're still talking megabytes at that point. So that's very cool. But listen, we're not here to talk about Hubble. You said a minute ago, when I said a space telescope, I said, no, this is the space telescope. So what's so the about this one? Why is this one so big? Why is it so important?
So I think just the ambition, first of all, behind James Webb. It's one of these things where we have no idea how we're going to do this, like you said, but let's just have a crack at it anyway. And that, of course, takes a massive team to kind of put together. So James Webb is a collaboration between several space agencies. NASA, of course. We've got ESA as well, the European Space Agency, and also the Canadian Space Agency, who's kind of your ringer outsider coming in there.
It's at that point that people sort of say, did Canada have a space agency? And of course they do. They were famously, as someone who has Canadian citizenship myself, alongside the Australian, immensely proud in the space shuttle era of, Canada were the ones who built the arm, the big space arm thing that went out and grabbed satellites and stuff. And Canada went, yes, that's ours. And there was a Canadian flag on it. I don't know if Canada's done anything else in space ever, but I do know that they did the arm for the space shuttle, so that's kind of cool. It's nice that they're working on this one too, so that's good.
Yeah, they have had other satellites and so on that sort of have been smaller scale, but I think this is the first kind of massive thing of this nature. Well, to be fair, it's the first big telescope launch since, well, I guess Kepler was probably the last even remotely large telescope on this scale.
When was that?
So Kepler was 2008, 2009, it started science.
So it is a big telescope. I mean, Hubble is, like, it's got a mirror on it which is about my size, right? Doesn't Hubble have sort of a couple of meter wide mirror?
Well, actually, there's a lot of really good facts that you need to know about James Webb.
All right, let's do fact time then.
Well, I'm going to call this, and, copyright if it doesn't already exist. This is going to be the stat attack.
Stat attack. We need a theme for that. We should have, like, sirens going off or something. All right, stat attack. Stat attack. Hit me.
So I'm going to give you a quick fire quiz and see how many stats about the James Webb Space Telescope that you remember.
All right, and kids, you can play at home as well. No cheating, no Googling allowed, because I don't have Google here in front of me. You're not allowed it either. So, Emily, let's go.
Right, let's start with how big it is. How big's the mirror on James Webb?
James Webb, I know it's big because I have seen pictures, but I'm not quite sure how big. I'm going to say like 4 meters.
6.5.
6.5 meters. Okay, so that is like 3 and a bit times me tall, because I'm just shy of 2 meters. So, wow, that's big.
Yeah, so Hubble's 1.8. This is 2.7 times bigger than Hubble.
Right. That's a big ass mirror. Wow.
Really big.
I've got so many questions already. Okay, next.
Right, okay. So if the mirror is 2.7 times bigger, how many more times powerful is it than Hubble? This is your maths question.
Hang on. Okay, so when you say powerful, what are we measuring that in? What is
the capacity to look at things, shall we say?
Well, I'm going to say that diameter is a linear thing, but size of mirror is actually an area thing. So if it's, let's round it up to 7 meters as opposed to 2 meters. So I'm going to say it is, let's say 3.5 times the diameter. Yeah, is that right?
Yep.
3.5 times the diameter. So I'm going to go that squared. So that's going to be, let's say, I don't know, sort of 12 times?
About 100 times more powerful.
100? How does that work?
So you've got the area, which is exactly what you calculated, which is well done. So that's very important.
PhD in mathematical physics helps.
But you've also got efficiencies. So you're talking about efficiencies in actually collecting the light and efficiencies in recording the light as well.
Yeah. Because to get from just the square of the area, which is in the order of, say, 10 to 15 times, then up to 100, that's a lot of efficiencies. They've designed the hell out of this thing, which is good to know because it has been a while. So, yeah, that's good. All right, next stat.
Cool.
Hit me.
What's the mirror made of?
Okay. I'm going to say it's made out of mirror stuff. What a mirror? Something really shiny. Emily.
What color is it?
It's sort of goldy, bronzy color.
It's gold. It's gold. It's got a coating of gold on top.
Seriously?
It is, yeah.
Did they do that just because they could?
No, it's not for the bling bling.
Do you know what we should do? We should make it out of gold. Why? Oh, we got a bit of budget left over. Wow.
Yeah. So it's actually beryllium is kind of like the structure of it.
Right.
And then it's coated in gold.
Is gold particularly mirrory? Like, I don't remember hearing about gold mirrors before.
Well, you can polish it up to be really shiny, which is part of the usefulness. But what's also great about gold is that it's very inert. It doesn't like react with all the sort of bits and bobs out there in space. So
have they ever made gold coated mirrors in space before? Is this a new thing?
I think there have been. I can't recall them off the top of my head, but I think there has been one or two. Yeah.
It looks good, though. If you haven't seen the pictures, check out the show art, the chapter art in this particular episode, and go and look them up online. This is a good-looking telescope.
Yeah. So you've got about nearly 50 grams of gold on the mirrors.
It's not a lot.
What's the value of that?
I don't know. Value of 50 grams of gold. Okay, well, 50 grams, that's like a Mars bar, right? So a Mars bar, that's quite a lot of gold. So I'm going to say the gold for the James Webb Space Telescope is worth a couple of million.
Ooh. Yeah, I'm glad you're not in charge of purchasing for the JWST.
What's it worth?
At current gold prices is about £2,000.
Oh, that's what I meant. Shows how much I know about gold. Right. Okay, so a couple of grand's worth of gold.
Yeah.
in the shape of a Mars.
Well, let's carry on with money then.
Yep.
How much does James Webb cost?
Oh, this one I do know because I actually, despite myself, Emily, not my usual form, I actually did some research for this episode because I was curious about the whole timeline of the thing. I know that the original budget was $500 million, and it looks like by the time it actually lifts off safely on December 18th from the launch pad, it's going to be in the order of 10 billion.
10 billion. The most we've ever
10 billion
spent.
with a B. And that's a lot.
That's
a lot of cash.
It is really a lot.
But then again, you put it in context, that's about the same price as a couple of fighter bomber jets. So,
And, well, yeah, how much did Hubble cost, do you know?
That one I don't know. I know it was over budget because it was over time, but I don't know how much. You tell me.
About $1.5 billion in 1990.
So that's got to be in the several billions by now.
Yeah, so not totally dissimilar.
Not dissimilar, especially when you consider this one is the big one. Like it really quite takes away Hubble in terms of size and scope and ability and all of that. So
yeah,
bang
but
for
if you want to compare it to more contemporary space telescopes, Kepler.
Yeah.
Do you want to have a guess at Kepler?
Oh, I don't know. I'm losing all perspective at this point. You tell me.
Kepler was about 560 million.
Right, $500 million. Yeah.
Yeah. TESS, our favourite planet hunting telescope.
TESS was like budget bargain spacecraft, wasn't it?
Absolutely,
like,
yeah.
What, couple of hundred?
200 million.
Yeah. Wow.
Pretty significant.
So we're talking a lot of TESSes equivalent. Yeah. So they really want this one to launch properly.
Oh, yes.
Yeah.
Very good. All right. So how big is the James Webb Space Telescope? And by this I mean kind of basically how big is its shield, its heat shield.
Right. Yeah, because we should at some point, I guess, talk about the shape of this thing, what it is. So we've already talked about the mirror, the big mirror thing, big gold thing, which we can talk about in a minute, which is, what did we say, 6.5 meter diameter, right? Big thing. Now, the interesting thing, Hubble is kind of like a big long cigar tube, right? It's like a big tin can with a flip-up lid on the front. I mean, Hubble to me is hilarious because it kind of looks like a kid's drawing of what a space telescope might look like. Right? It's a big telescope tube with a flip-up lid on the front. This one does not look like that at all. Like it doesn't look like anything you might recognize as a telescope. So it's got a big mirror-y thing on top. And then underneath that, there's, what is it? The solar shield?
Yeah, the heat shield. So it protects the mirror from getting too hot from the sun.
Yeah, which is like it's kind of a multi-layered baffle thing, which kind of I feel like is sort of a couple of times the size of that. So I don't know, 20 meters long? I don't know.
It's not a bad guess, actually.
Yeah?
Yeah, it's about 21 meters by 14 meters, which is about the size of a tennis court.
Right, okay. So tennis court-sized big space telescope thing with a really weird shape to it. Okay, I was not far off.
Yeah, that's very good. How much does it weigh?
See, this is really hard, right? Because they have to make it as light as possible because every gram that you put on board a rocket increases the cost of getting that thing into orbit by some ludicrous amount. So I have literally no idea. I can tell you, though, Emily, that there is about 50 grams of gold on the mirror, and so it's more than that.
Excellent.
Right?
Good deduction.
But beyond that, I don't know, a couple of tons?
It's about 6.2 tons.
Okay.
Yeah.
Roughly 1 ton per meter diameter of the mirror.
It is the biggest space telescope we have ever put up there.
Wow. How big?
By quite significant amounts, I think. I haven't got all the stats in front of me for all the others, but very much significantly heavier than all the others.
So this is a big deal, both to build, to test, and to get off the ground. This is hard.
Oh.
This is difficult science.
There's going to be a lot of very, very nervous people on the 18th of December.
And all of the people financing it and all the government people in multiple countries around the world just going, please, God, let this work.
Okay. Where will it live?
In space. Yeah. Got that one? Next? No, you're looking at me. Okay. Whereabouts in space? All right. Well, Hubble, this is the thing that always gets me. I always, in my mind's eye, Hubble is like right out there, right? Hubble is out in space. And as someone who's not an astronomer, it actually makes me laugh at my conception of what out in space means. So in my mind's eye, Hubble is out there like somewhere on its own in orbit around the sun, presumably. And no, of course, when I think about it, I've seen pictures of Hubble and you can see the Earth just down below it. Is Hubble in sort of a fairly low orbit?
Yeah, well, you know that astronauts have been to it, right?
Right, of course, because they had to service it. Yeah.
So it's not dissimilar to the International Space Station.
It's actually only just up there, right? It's not far away. You could walk to it if you had the inclination. But this is not the case with JWST, right? JWST is not going to be just up there. It's actually going to be a really long way away. And I'm going to say it's at, is it L2?
It is L2.
Which is a Lagrangian point, which is a mathematically defined point in space where it's got something to do with the gravity of the Earth and the gravity of the Sun. I'm going to have to hand over to you at this point. Emily, what's L2? Remind me.
L2 is one of the Lagrangian points. Well done. So there are actually 5 Lagrangian points. And what they are, I guess a good way to think about them is they are orbits around the Sun that go at the same rate around the Sun as we do on Earth without being on Earth. Right.
Okay. So it's not like L1 is the Earth. Is that?
No.
Okay.
I guess you could call it L0.
I guess you could. That would make some kind of neat sense. So these are points which you can orbit and you're going at the same rate as the Earth?
Yes.
Right. And so your position relative to the Earth kind of stays fixed in a sense. You're going around, but not like the moon is going around the sun kind of with the Earth, but it's orbiting the Earth. This is different to that.
No,
it's
they're
not
still
in orbit
orbiting the
around...
sun.
Right.
Yeah.
Okay. So tell me about L2 then. Where is that?
Yeah, so L1 is kind of a little bit in towards the sun from where we are. L2 is a little bit further out from the sun from where we are.
Right.
And so you've got the gravity of not just the sun and the Earth happening on there, which is kind of pulling it towards the sun, obviously, but you've also got gravity of some of the outer planets which tug along as well. So
right. Oh, so you actually have to take into account the other planets as well.
Oh, yeah, for all of these things to keep stable orbits.
Bloody hell. I mean, I would have thought we'd be close enough to the Earth that it's the Earth and then the sun, because the sun just dominates everything. I would have thought that'd be enough. But no, of course, Jupiter and Saturn and what other planets too? Mars? Like, do you have to...
Mars, I guess, to some extent. These are all secondary kind of gravitational effects. But yeah, you do have to be a little bit aware and be able to correct for when, things get tugged a little bit.
But to first order, as we like to say in physics and maths, to first order, is it that, the further away you get from the sun, which is the thing ultimately we're talking about, we're orbiting around, right? The further out you get, the longer it takes you to do an orbit. And so if you were to just dump the James Webb Space Telescope out at this L2 type place, forgetting about the Earth, it wouldn't go around at the same rate as the Earth because it's further out. It ought not to. But when you take into account the Earth's gravity as well, then that increases the overall gravitational effect, and it means that at that position, it's then going around at the same speed as the Earth.
It's like we're kind of tugging it along with our gravity as well.
Okay, nice, cool. Yeah. Why are we putting it there? That seems like a far more complicated thing to do than we did for Hubble.
Well, it's very convenient because it means it's going to follow us around the orbit around the sun, right? So
we don't want to leave it behind. I get that much. But this seems really quite... I mean, you could just put it in orbit around the Earth. Why aren't we doing that?
Because the sun is a really tricky thing. So you want to keep... And of course, the moon's really tricky as well. So when you have space telescopes like Hubble or TESS that are in Earth orbit, then you've got to do some really interesting calculations, first of all, to keep them there. Hubble, for example, has to keep boosting itself so it doesn't slowly, decay and crash into the Earth.
Burn up on re-entry, yeah.
TESS does some really clever things with the moon's gravity to keep itself in its orbit. But there are lots of places you can't look. And even places you can look, if you've got Earth shine or moon shine, or it's tricky. You've just got to be careful. So when you want to do really deep space stuff, you just want to go somewhere nice and dark.
Right. So the idea is to get as far away, while still being connected to the Earth, you want to get as far away as you can so that you can go, we're not being outshone by all the earthy stuff here. We're at a decent distance. How far away is L2?
It's 1.5 million kilometers.
Big numbers. Hard to get a grip on that. How far away is the moon?
In kilometers. Don't know.
Just trying to get a grip for, is L2 inside the moon orbit?
Oh,
distance?
No,
outside.
Yeah.
Right, way outside.
Way
okay,
outside,
so it's a long way away.
Yeah.
Right, okay. So
1% the distance of the sun.
Right. So this is a long way away from the Earth, but in close contact because of this L2 position, that it's always going to be just up there. So is it like, in terms of our orbit around the sun, is it kind of like fixed in place? Do we sort of put it out there and go, okay, you're done?
Yeah, pretty much. I mean, when we talk about going to L2, they don't sort of sit there. Isn't this kind of little tiny point and you sit there and that's fine.
And lock it in.
Spacecraft orbit L2 technically,
right?
But it's that's roughly what they're doing, is just orbiting this imaginary point.
Are there other spacecraft?
I was going to say
this?
there are some. There are some friends out there for.
Oh, well, that's nice.
JWST. You probably know of quite a few of them.
Do I? You said with doubt. Go on.
So you got Herschel.
Okay, Herschel's out there.
But,
cool.
Defunct, but
yeah.
there.
But hanging out.
Planck.
Right.
Planck's still going.
Yeah.
Gaia and Kepler.
So there are a few.
Yeah.
Yeah,
I mean,
we know
some
how
of
it
these
is.
will be decaying because they're kind of old now.
Yeah. You said there are 5 Lagrangian points. Mm-hmm. So there's one closer to the sun, one further away from the sun in sort of a direct line sun. What is it? Sun L1, Earth L2.
Yep.
Right. Where are the others?
So L3 and L4, I can't remember which way around, but one of them's ahead of us in our own orbit and one of them's behind us in our own orbit.
Do we use those?
We have put stuff there before. I can't recall anything right off the top of my head, but yeah, you can put things in Earth leading or Earth trailing orbits.
Right.
L1, we put some of the solar observatories. So SOHO, for example, is at L1. And there's L5, which is directly opposite us in our own orbit.
I can see a problem with that one, and that is that if you were to put something out there, you'd never see it again.
Yeah.
Because there's a big sun in the way, and it's always going to be in the way. So, yeah, maybe not L5, but the others, potentially useful.
Yeah.
Yeah.
I think there's some solar observatories
Right.
kick around. So there was SDO, for example, that was moving around in the orbit as well. So, some of them do get used for those kind of purposes.
Cool. Okay. But the point, I guess, for the immediate conversation is we've used L2 before. This is not brand new. So getting it up there and into position shouldn't be too hard.
Well, yeah.
On the scale of things,
Well, here's the next question then. How long is it going to take to get there?
I mean, look, I was flat out even getting a scale for this thing. Like, is it closer than the moon? Is it further away than the moon? I don't know. So weeks? Several weeks?
About a month.
Yeah, okay. I'll take that as a win. I'll take that. I'll take the point.
Take a couple of days to get to about the distance of the moon and then, carrying on. It gets harder the further you try and go out, because this is the thing, you've got to get more energy to go further out in the solar system.
Yeah.
Right. So when we go in, we've got to dump energy. When we go out, we've got to gain energy. So you kind of got to and make sure you get just the right amount, so that basically it's like, I saw a nice analogy for this actually. It's like cycling up a hill. You've got to push just hard enough so that when you get to the top, you can just get there and then stop, not go over the other side.
Yeah, not go over the side and keep going on forever. And everyone waves goodbye to this $10 billion satellite as it goes off to join Voyager. Yeah, that wouldn't be good. So, yeah, you need a bit of energy, but not too much energy, and then get it out there. And presumably it's got like some little thrustery things on board to just sort of, just stop there, stop. Okay, now get yourself in position and turn around and all of that.
Yeah, and you need to do sort of small corrections throughout the course of its lifetime anyway.
Cool. Okay, any more stats for the stat attack?
Okay, so it's going to arrive in about a month, so sort of January next year.
Yep.
How long till we get some science out of it?
I've got nothing. I have literally no idea. So I'm going to say a week.
Oh, I wish.
I don't know.
It's going to take a week just to start turning things on, I think. It's going to be about 6 months. So
Right.
mid
Okay.
next year.
Okay. I mean, I'm thinking back to the LIGO experiment, which was the one that was looking for black holes, colliding black holes, right? The gravitational waves experiment. And when they turned it on to do some tests, they went, wait, what was that? And it was a colliding black hole. And like no one expected it to do anything at that point. Like they would be waiting forever. And it's like, no, there's one. There's a colliding black hole. Yeah, write that one down. And that was really surprising. So for all I know, you could put JWST up there and it unfolds itself or whatever and goes, look, there's a thing. And it's, oh, quick, write that down. I don't know. I have no idea. So how long before?
About 6 months.
6 months.
Well, at least for the sort of scheduled science program. Of
Right.
course, there will be testing and commissioning before that. And so, yeah, those sorts of things could happen during commissioning. You could see some exciting stuff. But yeah, the official one, that's just kind of like everyone submitted their ideas. Please look at this for me. Yes, all right, we'll look at that for you.
Okay. Yeah. So that all kicks in sort of northern summer next year, all going well. Cool. Okay.
So how many people did it take to build, James?
I mean, at least a few, right? So it wasn't like some dude in his shed. So these collaborations tend to be enormous. I'm going to guess in the high hundreds.
1,200 scientists and engineers physically involved with building the
Yeah, okay. I would have said a high hundreds, maybe up to 1,000, so I was under by a little bit. But that's a lot.
People from 14 different countries.
Yeah.
There's, although we're talking about, 3 main sort of areas or countries of space program, it's much more global than that.
Yeah. And over a long period of time. So, there's going to be a lot of very nervous people on my birthday.
Oh, I think so.
It's going to be good.
My last one.
Yep.
What wavelengths is James Webb going to be observing?
Now, okay. Hubble, you said a minute ago, was in the visible into the IR, into the infrared, yeah? And now, if I remember this correctly, James Webb is going to be focusing somewhat more on the IR and somewhat less on the visible. So there's an overlap, but it's kind of down in the red end of the visible and very much in the IR. Is that right?
Absolutely.
Yes.
Yeah, very, very red.
Scores the final point.
So I've got my numbers here in microns, but I can convert them as well.
Sure.
So microns, which is micrometers, then you're looking at 0.6 to 28.5.
Okay, and so when we're talking this is length measurement. So this is wavelength of the light that it can see. So say that again. It's what?
0.6 to 28.5 micrometers.
Okay.
So, I mean, in normal sort of optical human speak, our visible range is kind of somewhere from 400 to 700 nanometers. So 0.6 microns, about 600 nanometers.
Right. So it's quite a long way up into the red, or down into, depending on which way you're looking at, into the red end of the rainbow, off the scale into the infrared part. So why are we interested in that?
Well, this is the exciting thing. So whilst we sort of see Hubble as kind of like an extension to our eyes in space, James Webb is going to be largely seeing stuff that we can't see with our own eyes.
Right. And we're used to that because like so much astronomy over the last 100 years, I guess, has been across so many parts of the spectrum, of which visible is only one tiny bit. But we've got radio astronomy, we can't see radio waves. We've got X-ray astronomy, we can't see X-rays. We've got the IR and the UV and so on. And the visible is only one little bit. So that's nothing new. But why IR? What does that get for us?
Well, I think it's just all tied up in what the science goals of James Webb are. And I love this because when you sort of go and look at the sort of the science themes and everything's really nicely laid out and you've got these wonderful questions that we're going to solve about the universe, you look at kind of the 4 themes. And I'm going to tell you the 4 things. I'm going to get you to tell me what you think about this collection of 4 themes.
All right.
And we'll look at them each in detail, but let's just start with what the 4 are. First one's early universe.
Mm-hmm.
Second one's galaxies over time. Third one is star life cycles. The 4th one is other worlds.
There's a lot there. That's pretty much everything from planet through to the universe.
Yeah.
So that's everything in space.
Yeah.
Right.
That did make me chuckle a little
Presumably
bit.
including along the way space itself.
Absolutely. Oh, yeah. Don't worry. We're going to use all the buzzwords, dark energy, dark matter, black holes. Everything is in there.
Right. So I guess the point is this is a big, ambitious telescope which is going to be able to tell us a lot about pretty much everything.
Exactly.
Cool. Okay. I could see why people would be interested in that.
But there are some very specific reasons why you might choose the IR to do all the parts of these different areas. So if we start with the early universe, so let's have a think about what we know about the very, very early universe. You know what some of the earliest sort of galaxies that were born first in the universe and what we can see as the most distant galaxies. Because when we look very, very deep into the universe, we're looking back in time because that light has taken so long to travel towards us.
Yeah.
So do you know what some of these really early galaxies are?
No.
We tend to call them quasars.
Ah, yes, I have heard of that.
Quasars, yeah. So these are really, really bright, extraordinarily old, I guess now today.
Yeah.
So very early galaxies in the universe. And they happen to be extraordinarily red.
Right. And that means that they are very, very far away.
Exactly.
Which also means, as we just said, very, very far back in time. Presumably also means kind of hard to spot.
Well, unless you're looking in the very, very red. So these things were so red that when we first started looking at these objects in the sky, we didn't even recognize what we were looking at because they had we were looking for like spectral lines of different chemical elements and trying to figure out. Now, the spectral lines are normally at these particular wavelengths. And we're looking at these objects and saying, this is just like nothing we've ever seen before. What are these crazy things? And it took quite a while for us to realize, oh, these are all the same chemical elements, the same spectral lines we love and are used to. They are just shifted from where we're used to them being so far into the red that it's just extreme red shifting.
Right. And the red shift, that's the thing that astronomers use to determine like how far away and how long ago things are, right? Because the expansion of the universe being that the further something away is, the further it's receding from us, which means the redder it seems is the Doppler type effect.
Yeah, so imagine a photon. So if you can imagine like a little piece of string, which represents a photon. It's a wave. It's got a wavelength. But as that photon has travelled from its point of emission in this galaxy many, many billions of years ago to arriving on Earth today, then over that time, the universe has expanded. So it's actually slowly stretched out that string and made the wavelength longer, which means a blue photon that was originally emitted billions of years ago has been stretched out and now becomes a red photon.
Right. And so that's shorthand for if these sort of fingerprints, these spectra were shifted so far down to the red in these quasar things, whatever the hell they were, that must mean it's not something brand new that we haven't seen before. It's stuff that we have seen before, just really far away, which means really long ago, which means what? That these are some of the original galaxies in the universe.
Some of the really early galaxies in the universe. So,
right.
Yeah, it's really exciting. And so to observe those things, you need to go really far into the red.
Yeah. Well, unfortunately, we have a machine to do that.
Well, exactly. And a really powerful telescope as well, right?
A rocket launch pad near you. Yeah, so that's good. Okay, so early universe, you can see why you'd need the IR there. So that's one, tick.
Next one is galaxies over time.
Right.
So this is, I guess, related because, like we said, quasars are kind of really early types of galaxies. But this is more sort of trying to draw the link between what we might see happening a long way away, in the very early universe, to what we see now in the modern universe around us. How did we go from what we normally see as these very early galaxies being these kind of little clumpy, kind of messy things to the kind of really big, beautiful structures that we see around us today.
Like our own Milky Way.
Like the beautiful spirals,
yeah. And some of them are amazing, an incredible structure. But as you say, very, very different from these clumpy. And is that true of the early ones that we see? That they're just a blob. You just throw a bunch of stars together and that'll do. That's a galaxy.
Well, we've only got a few, but that's what some of the very, very early ones look like.
Right.
And there's kind of an even question of how do you even make a galaxy in the first place, right?
Why is that a problem in the early universe?
Well, I mean, there's a question just how big a cluster of stars make a galaxy.
Oh, I see.
You got your first stars kind of turning on in the very early universe. Were they already in smaller structures of galaxies, or did the structures of galaxies come a bit later?
What's the order of scale here? Are you having stars forming and then going, oh, let's get together and make a cluster, let's make a bunch of stars, and that's a galaxy? Or is it that they're forming on the galactic level and then the stars are turning on? Like, do we have answers for any of those questions, or is that what this is
Only
about?
very, very initial answers,
Right.
yeah. So we think, probably stars came before galaxies, but we need to kind of do some more research on that.
Yeah, okay.
And then you think about the sort of very complicated history, a few billion years or 10 billion years is a long time for stuff to happen.
Yeah, that is a long time.
So when galaxies were formed that many years ago, there's been a lot of change since then. And we can see some of that change, particularly in interactions between galaxies. Galaxies love to merge and kind of eat each other up and do all this kind of stuff. So how important is that to understanding how galaxies evolve?
Right. Now, I can see how, look, if you're wanting to look at evolution over time, and the old ones we've already established, it's really good to look at them with the IR. Does that carry through to more recent times? Is it useful to have a JWST type telescope to look in more recent times at galaxies as well?
Yeah, absolutely. We've got some really, really old red galaxies that are in the modern universe as well. So these are galaxies that we think probably went through mergers some time ago, used up all the gas and dust so that they don't have any new stars being formed. So all they're left with are kind of really old red stars. And so obviously looking in the red to those kind of galaxies is very, very useful as well, studying them.
Cool.
But yeah, I mean, even on this whole scale of, say from start to end of galaxy evolution from then to now, how do things like dark matter play a role in that whole process is a really important question.
Yeah.
So let's just throw in some more, giant questions in astronomy.
Yeah, just throw that one in as well and put a tick in that box. Yeah.
So I think, how do galaxies evolve, live, and I guess spend the rest of their lives is the summation of that.
Sure, just a small research project there. Okay, big tick in that one, right? What was next?
Star life cycles.
Right, so we've gone from the universe, early universe, to galaxies, now to stars.
Now, the big one here that is actually looking at life cycles is more focused towards the early lives of stars. So how do stars form and how do they sort of affect their environments around them? And the reason why this is such a big question to be looking at in the infrared is because stars form in these really big clouds of gas and dust, which actually are quite cold when they start to come together. If they're too warm, then they've got too much thermal energy and the cloud doesn't collapse. So they have to be quite cold to get that. But cold gas and dust is very opaque.
Right, and hence, there's a lot of really beautiful Hubble images of lots of gas and dust and things, which make fabulous images. But the whole point about them being fabulous images is that you can't see through them. You can't see through all the dust. Is that?
Yeah, exactly. Yeah, think about some of the real classic Hubbles. So you think about the pillars of creation, really classic Hubble picture.
Yeah, those fingers. Yeah, they're amazing.
You think about things like the Horsehead Nebula, for example. Yeah, lovely big clouds of gas and dust. Can't see behind them.
Right. And so we can see those things, but if you actually want to see into them to what's going on in there, you can't do that in the visible, but you can with the IR?
Yeah, so the visible light's blocked, but the infrared light, especially when you start moving slightly further into the infrared, can actually penetrate those clouds. And so you can actually sort of, I guess, is it spying on
maybe
little baby stars being formed?
Pulling back the veil. Yes, peeking through the curtains. That's getting a bit weird. No, let's not go there. But you did share with me before we started recording an amazing pair of images, I guess, both of which were taken by Hubble.
Yep.
Yeah, but one is definitely in the visible and one is definitely in the IR. Same bit of space. What are we looking at in that? I'll make that should be the chapter art. You should be able to see it right now on your podcast player of choice. So
this is Carina Nebula,
right?
And so at the left-hand image, as you say, is the optical image, and this has got your beautiful colors, and you can see those big clouds of gas and dust, but you can't see what's going on inside. And then when you see the IR, you start to see all these little stars jumping out that are being formed right deep down inside these clouds.
So you lose all of that sort of detail of the dust cloud that makes it beautiful to us on one level. It's amazing to see that structure. You're kind of losing that, but what you're gaining is the ability to scientifically look inside and say what's going on in this previously hidden bit of the universe.
Yeah.
And that's what you can do with IR because it can look through the dust.
It's a bit like an X-ray, isn't it?
Yeah, nice.
The dust clouds aren't unharmed by this process.
That's right. No dust clouds, no baby stars were harmed.
So that's one of the big things, and that's why you need the infrared, and that's why you need big, powerful telescopes to be able to see, get lots of light, etc.,
Gotcha.
etc.
Now, this does lead me to a question. When you sent me that image, it actually made me think, one of the amazing things about Hubble is all of its science aside, it gave us almost a visual language in the universe. People were able to look at the universe in ways which we had never seen that kind of detail before. We were able to see things like the pillars of creation and go, blimey, look at that. There is structure out there that you cannot believe. Because we're able to see, in a lot of cases, the structure of these clouds. Does this kind of mean that we're maybe not going to get the same kind of visual impact from JWST? What do you think?
This is something I've really thought about. So when you think about Hubble images, if you remember the Hubble Heritage sort of images, so the really early ones that came out in the 1990s, they're very distinct. You can tell, like when you've seen enough nebulae and so on, you can tell an old Hubble image versus a new Hubble image.
Right.
First of all, you can see like the old mosaic checker pattern. So you sometimes see these black squares creeping into the image, which is just the camera. But, they're not quite as sharp. And actually what's really interesting, I find, is the color choice. Mm-hmm. They had the Hubble color palette, which was a choice of colors so that they said when we take an image in this filter, say oxygen, it's going to be red. When we take an image in this filter, say hydrogen, it's going to be green, et cetera, et cetera. And so there was this really distinctive look to the Hubble pictures. Now, since then, actually Hubble data is freely available online as well as all their color palettes that they've chosen to use over the years. But you look at a modern picture, and there's some really nice examples of these, which I'll share with you so you can share with the listeners. They're sharper, So they've got the upgraded cameras and so on are all very lovely. So you get sharper, bigger images. But the color choices are also quite different and much more, I guess, modern in a way. Lots more blues and purples rather than greens and reds. Now, that's just a choice, right?
Sure.
That was just a choice. It's not something we're going to see with our eyes. We can't see lots of the filters that Hubble uses.
So what you're saying is, if I may paraphrase, in a sense, these pictures are lying to us. This is not the way the universe actually would look if we could look with our eyes. We're making choices here about if we look with this filter and then superimpose that with looking with this filter and then with this filter, we can make choices about how to bring those patterns and designs, how to bring the structure out in different ways that are pleasing or instructive to our eye. But that's a choice.
Exactly.
We can do that however we want. We could do it in black and white. We could do it in rainbow colors, any way we want to.
Yeah.
And that's not representative necessarily of what we would actually see with our actual eyes if we were able to.
No, and even the color response, if you like, is very different. So they have images that have taken half an hour to take in the blue, but only half a minute to take in the red. And obviously your eye can't do that. Your eye takes one exposure in all colors. It's more sensitive to some colors than others. It's more sensitive to greens, for example, so you're more likely to see green colors. So in a way, these are not visual images anyway.
Sure. Okay. So taking all of that, what does that then mean for anything? I guess what I'm asking is, are we going to have a similar kind of new public-facing view of the universe from James Webb in a similar way to the way we had with Hubble?
I think so, but I think it might be unexpected. So I think there's going to be some very deliberate choices about some of the targets that James Webb's going to do, particularly in the commissioning phases, because they want to get some, let's say, pretty pictures.
Yeah.
Right? You got to
Make it
sell
seem
this.
like it's worth our while, which is hilarious, right? Because that's not what it's for. Right? It's not for making posters that teenagers can put on their walls or we can put on our computer screens. That's not why we spent 10 billion. But it's a really important part of selling this emotionally to the world.
Absolutely. And you think of the billions of people around the world who in some way have contributed this and through their tax-paying money. It's important
I want
to
the
do
pretty
that.
pictures, damn it. I want a screen background, thanks.
So even though these photographs may be taken in cameras which don't even look even remotely in the same kind of wavelengths as our eyes, I think we're going to see some glorious images nonetheless.
Cool. Something to look forward to. But, I mean, as we said, that isn't really the science point. So let's leave the pretty pictures and get back to the science. Did we make our way through all of them? We didn't, did we?
We got one more.
Got sidetracked. So we did the universe, at the universe level, early universe. We did the galaxy level. We did the star level. So that really only leaves us with things that are smaller than the level of stars, which is planets. So what are we going to learn about planets?
So the other worlds theme.
Yep.
So of course James Webb is going to be a planet hunter because every telescope is now.
Because why not?
Yeah. Everyone wants, their own pet private planet.
Exactly.
I shouldn't have tried to say those three P's in a row. So it's going to look for transits. But honestly, I think, even though that's being said, don't think that's a real major part of the goal.
James Webb, it's kind of like, could you do this? Yeah, we could do that. All right, write it down. Yeah, no worries. We've got transits too.
Yeah. I mean, to be honest, James Webb is not a planet hunting telescope.
Right.
It's not built for that. It would be a waste of its time to do that. We've got dedicated...
It's below me, it says.
Well, it's not designed in the same way as the planet hunters like Kepler, like TESS, like
Sure.
all the ground-based surveys we're doing. I mean, in fact, if you think about TESS itself, TESS is clever. I mean, this is a point that James Webb took so long to build that TESS wasn't even imagined when James Webb was started being built.
Look, you guys are taking so long to do this. We're going to make our own telescope. Put it up there before you. Come on.
But TESS was designed to be complementary to James Webb.
Right.
Because TESS is a survey telescope. It's scanning the sky. But it does have two what we call continuous viewing zones, which means you get kind of a year of data at a time from these continuous viewing areas. And those zones, guess where they match up to? Continuous viewing zones of the James Webb Space Telescope.
What are the odds? What are the odds of that? I'm guessing that these teams talked to each other a bit in the lead up to all of this.
Well, it's just one of those things. These are the places in the TESS field of view that we're most likely to find exoplanets. let's put them in the place that's easiest for James Webb to follow up on them.
Kind of makes a lot of sense. Yeah. So Tess is doing all the hard work, and then James Webb, gets to come in and take all the glory? Is that how that works?
So I think it's going to be much more focused on follow-up
Right.
of these exoplanets. And follow-up in the infrared means doing, I guess, two things. First of all, you're going to be looking for doing a bit of spectroscopy on them. Now, why you want to do spectroscopy on exoplanets is to look for atmospheres.
Right. Yeah.
See what they're made of. James Webb's going to be quite good at that. Particularly in the infrared, where you get to see lots of molecules. That's where they like to hang out.
And molecules can mean all sorts of interesting things. Molecules mean chemistry. Molecules can mean interesting chemistry, maybe even organic chemistry, maybe even interesting stuff happening within the atmosphere. That's fun stuff.
Maybe even biosignatures.
Yeah,
Who knows?
yeah.
If we can agree on what the biosignatures are. then-
Yes. If we can just measure it and then we'll argue it out. Yeah.
So it's definitely designed to be doing that. I think that's one of the biggest parts of the funding, I guess, behind James Webb comes from, can we actually investigate these exoplanets and find life?
Right. So that's a big part of the argument, because I would have thought that, all the other stuff from an astronomical point of view, there's a lot of people leaning on, let's look at, grand scale universe stuff, let's look at galaxy stuff. But maybe actually, given how big the whole exoplanet thing has become over the last couple of decades and really exploded in the last decade and a bit, maybe that is one of the biggest arguments you could make for this thing.
Absolutely. Exoplanet science is so sexy right now. You've got
yeah.
so many people working in this field, so much money pouring into it. It's a natural thing that it should be a main focus of James
Sure.
Webb.
Hell yeah, we can do that. Yep. Throw us some money.
So we've got that. We've also got planet formation for the same sort of reasons as we mentioned for star formation. If you can see stars forming, planets form at the same time.
Sure.
That's quite important. And I guess something I hadn't even thought about, which is very rude of me, and I'm very sorry to everybody who works in these
Yeah,
fields.
come on, Emily. What? What is it?
Solar system science.
Oh, as in our solar system, or
Yeah.
just right? I guess I don't really think about that, but of course, you think about Hubble, and it looks at things which are very, very far away, but it also is perfectly capable of turning around and gazing at things fairly close by as well.
Yeah, and it has done on a semi-regular basis.
So James Webb can do the same thing?
Absolutely. Comets, outer solar system objects, going to be favourite targets. Even Mars, the atmosphere of Mars, it's going to do some looking at that. Other planets. Remember, think about it, at the moment, we don't have a lot going on, particularly in the outer solar system, in terms of space probes, right?
Right. Yeah.
We've sent a bunch of things to Mars.
Yeah.
Not much has gone further.
No, and the ones that did go further have gone much further.
Yeah.
Like they're just winging their way out into space now, and there's, bye.
Yeah.
So, having a big honking telescope out there which can peer out there and tell us what's going on could be kind of useful.
Yeah, because, since Cassini, we've not had that much.
Yeah, when was that?
I think that finished in about 2017.
Yeah, it's a little while ago
There's a James Webb page that needs updating then. Talking about that as if it's in the future,
Right.
which just goes to show you.
Well, it was at the time.
Yeah.
I'm amazed they had the internet, frankly, when they started all of this. Oh, dear. Okay, well, that takes us through all of the science goals then. We've ticked off basically everything from literally next door through to the very beginning of time and space itself. Well, not quite. We're not using this to look at the Big Bang, but early galaxies.
Basically from the very
Galaxy
first
formation
stars.
onwards. Yeah.
And that includes dark energy, black holes, gamma ray bursts, anything, everything
that
exotic
stuff.
you could want in the universe as well.
Wow. So, this one better launch. Fingers crossed. Right, well, I kind of feel like we've built up the expectation on this one, Emily. I tell you what, on December 18, I am going to be glued to the television, and it's my birthday. I can do whatever the hell I want that day. I'm going to be watching this thing taking off and just keeping everything crossed. This one better work. There's a lot riding on this.
To be fair, I think one of the reasons why we're here, why it's taken so long, is because we've triple checked, we've quadruple checked. We've checked that this thing works for the 20th time, and we're confident that now let's set it off.
Yeah.
It's good.
Who's launching it? Do we know what it's going on?
So it's going on an Ariane rocket.
Right. Okay. I think they've worked out most of their issues over the years.
Yeah. They're pretty good,
Yeah.
but nothing's 100%.
No. But it's not Elon. It's not.
No.
It's not Musk Incorporated.
No,
It's,
I think the payload's too big anyway for that.
Yeah, it's a bit bigger than the sports car.
Hmm.
Yeah. Well, look, fingers crossed, and huge shout out to the hundreds, well over 1,000 people who have worked on this over a very long period of time. If this one gets up there, you all seriously deserve a proper drink. And if this one doesn't get up there, make it 2. Make it, take the rest of the night off, yeah? We're going to be rooting for you. Emily, it's so good to be back. At the end of every show, what do? We tell people how they can contact us or something.
They can look at our things, those communication tools.
The interweb things. I think we're out there on the interwebs, and I'm going to make a commitment right here, right now. We will try to post on the interwebs.
Yes.
I know.
Yeah. Do you remember the password?
I thought you had the password.
Oh, no.
I'm sure I've got it here somewhere. Listen, Emily, how can people find us?
Yeah, so we're on Facebook.
We are.
So we're at Syzygy. If you just put in Syzygy, SYZYGY.
Well done.
And podcast and some
You'll
sort
find
of
it.
shiny things will pop up.
You'll find us. Go and click on the thumbs up thing and you'll hear from us whenever we post, which will be more often, I promise. We're also on the Twitters. We're in the Twitterverse at SyzygyPod, if I remember correctly.
It's about the same way.
Yeah. So go and find us on there. Send us a hello. And occasionally we post something on the Instagrams as well.
Yeah. Usually just beautiful pictures from somebody else.
Yeah, we'll go and put some of these ones of JWST up there this time around, and you can just see how gorgeous a machine this thing is. The other thing you can do, of course, is go to our fabulous website, where you can find all of the past episodes, all 80 plus of them, all of the show notes, all of the pretty pickies, and you can find the page of all of our supporters on there, and you can find a contact page so that you can get in touch and say, hey, love what you do. Have you ever thought of doing a show about this? And we'll go, cool, let's do that.
You might want to tell people what the
Oh, yeah, I probably should, shouldn't I?
URL is, yeah.
I really have forgotten how to do this. Syzygy.fm, go and find us. If you want to support the show, there's a bunch of ways you can do that. First and foremost, just tell everyone you know, right? Go and find people who you think might enjoy a bit of space nerdery and tell them Syzygy is the thing you got to listen to. Give us a review and some stars on your podcast player of choice. That really helps us to rise up through the noise. And if you want to become a financial supporter of the show, you can go to patreon.com/SyzygyPod and you can become a financial member. Help us to keep the lights on, the electrons flowing through the website. And as this world opens up back out into something vaguely approaching normal, we might be able to do some live shows again.
Woo.
That would be cool. That helps us to do that. Otherwise, Emily, it's so good to be back. With any luck, we'll be able to do another show in this very office really soon. What about a week's time? Should we try that?
I think that's perfect.
Done. In which case, I will see you then. We'll catch you all in about a week. See you, everybody.
See you later.
Bye. I don't know whether or not do you want to even mention the fact that people have been a bit up in arms about the name? Is it worth going there
I didn't
or not?
I didn't go there.
There's been some criticism because James Webb apparently was involved in the sort of McCarthyism era of getting rid of all the gays and the lesbians from the government, and so there have been 2 calls to change the name.
Right.
NASA has, at least until this point, said, no, we're not going to do that. Someone actually suggested that keep JWST, just call it the Just Wonderful Space Telescope, which I think that's okay, fine. JWST, we'll just go with that.